जी
Okay, so you guys get the first homework? Okay, so you won't be able to do, I mean, you might be able to do all of it, but there are questions that you haven't sort of, that you still won't be able to do if you just go and run it out, even after the first week. And so, but some of the problems given in there are just sort of remedial homework. You just get some homework on what you've been writing, or if you under pressure, sort of things that you're supposed to write. Things like on class completion, calendar reporting, calendar methodology and stuff. You'll be able to do that. If you're still not able to do that, go to the tutorial, and so you should be able to do those problems after that. There are other problems related to Noyer's theorem, and most probably will go through this the next week. And so, if you can't do them, there's no problem. You can sort of always have a go at them after we've had a discussion on Noyer's theorem class. So, but those problems are really easy, and you might still be able to do them. Mostly they're just calculating the argument potential. There will be another homework on Noyer's theorem in the next week or the week after. And there could be a quiz at any time, right? So it's not going to be announced, as always, both in GR and in QFT. It's not going to be announced. And so, but in GR we're going to just have the regular 4 or 5 quizzes. In this class we're going to have a lot many more. You start? Okay. So, if you guys remember, the last thing that we wrote on the board. So I was just trying to sort of show you that this is nothing more than doing another way of quantum mechanics. Okay? And so I have taken this example and I've written this electromagnetic field in a certain gauge. And so the vector potential can be written these two sums, K and R, this is polarization. These are all possible modes. And then there was this alpha and epsilon r. So this is characteristic of this pair. This is a vector. Gives you two polarizations. And you have this, what do you call that, coefficient of this mode, this particular mode, e to the minus I, negative e plus, and then you add this to make all of this real. Right? And so you'll always be able to do that. Can you see why you should always be able to do that? Do this with anything. Because these are just, what are these things? These are explanations, but these are wave functions of waving particle, right? So what you're doing is that you're just writing in a certain basic, which is the momentum basic. I should always be able to do that, right? It's just a function that you're writing in a certain basis. That's what a Fourier transform is. And so basically that's what you're doing. So and the reason we always do that is because it just decouples the modes. And so you can study the whole thing mode by mode by mode, and all of the differential equations in the free field sort of configuration, so they become algebraic equations. Very easy to deal with. Right? Separate out. And then you can, if you wanted to go back, you always take the inverse Fourier transform. You don't want to do that, but okay. So the first thing that we'll do today is, for example, and that'll also give us sort of a feel of how to deal with these things, is to calculate the Hamiltonian, right? Or the total energy. Does anybody know what the total energy should look like? Anybody else? By the way, whenever I ask a question, you don't answer it, you just raise your hand if you want to answer that question, then I'll let you. But here, total energy of the electromagnetic field. We just finished a course on electrodynamics last semester. By the way, we're taking C to be 1, and so sometimes that will just be 1. So in that case, what is T00 in this case? That you guys should know this one. Yeah, it's the energy density, which is E squared plus B squared, right? So it's just E squared plus B squared, and the Hamiltonian is just d3x, so it's 1/2 E squared plus B squared d3x, right? So that's what we're going to calculate. And you remember we're working in, where is E and the B field here? Yeah, where is the E and the B field here? Where is it? What happened? Okay, yes. What's your name, by the way?
Suhail.
Suhail, where is the E and the B field?
In A.
In A?
Extraction of A.
Yes.
Inside the
No, yeah, whatever that thing is. Yeah, that's right. I'm not asking physically where it is. We're just talking about the scalar potential. Where did these two come from? That's what I'm asking. So, okay, maybe I'm not asking the right question. So it's just there across A, right? But phi is 0. We're working in a gauge where phi is 0. So E must be 0, right? No? You guys are too good. Okay, so there is, so minus partial A by partial B. Anyhow, so this is what we're going to calculate, right? And most of the calculations, because of this monstrous expression, most of the calculations that you'll be doing, initially at least in final field theory, are just going to be very long calculations. And I won't be able to do them on the board. Okay, so what will happen is that I'll sort of guide you through the calculation, and then as a homework you will complete it always, in all possible detail. And I suggest that you use a bigger piece of paper. You can just see what happens now. So let's calculate first B squared. Okay, so B squared, so let's just calculate B first. So B is del cross A. The other is one. You are this one, right? Yeah. How do you calculate that? What is B? Yeah, do that. Okay, Zara, right? Sayyida Zara Nakmi? Mariam. Sayyida Mariam Nakmi? Okay, yeah, Mariam. Who's Zara? There is a Zara. Mariam Zara, okay. I saw that Mariam Zara. Yes. Okay. Anybody? Anybody? So what should I write? So K, R, alpha. You guys remember what there was in alpha, right? And so then there will be K cross epsilon R. That's it. There's an alpha. Right? And then there is this whole thing again, which I don't like. Oh no, I should write that. I should write that. Why should I write that? So this is a k e to the I k dot x e to the minus I omega t minus this minus a star k e to the minus I k dot x e to the I omega t. Right? And so b squared, and now things are going to get out of hand. So yes, how do we write b squared here? You're registered in class? No. 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 Oh, that's okay. Okay. So yes, you're registered. How would you take b squared? Believe me, if I ask you once, you won't forget it. If I don't ask you, and I just keep on going through it, you forget it. Yes. Usually when you have a sum written like that, and you want to take the square of the expression, what do you do? Multiply with what?
Sum of it.
Yeah, so how should I write it as a sum? So for example, this K, R, right? And this should be alpha I squared, alpha squared. So this should be K cross epsilon R. Now what? Dot K cross epsilon R? Right? Right? And then there will be an A of K e to the I, K dot x, e to the minus I omega t, minus A star K, e to the minus I K dot x, e to the I omega t, and then I write it again. A K, e to the I K dot x, e to the I omega t minus A star K. Guys, don't discuss among yourselves, it's just very distracting. Yeah. Is that okay? There's something very wrong with that, right? The cross term, yeah, you discuss it, right? So basically what is happening is that you have to have a sum over k prime and a sum over, let's say, s, right? And so this becomes an s. By the way, yes, there is an r here as well. You understand what is up? Because okay. So yeah, why is there an R with an A, with the A over there? There's a better way of saying that. A given mode is characterized by not just the value of K, but the value of R as well. Right? So when you say a given mode, it means K and R. You will have to specify both of these. Okay? And so this thing is going to depend not only just on K, but on R as well. Okay, and so, okay, so there is a K prime, and so there is an R here, and then there's an R here, and K, and then this is a K prime, this is a K prime, and this is an S, this is an S. Right? And of course, now when you open this up, you're going to have what, 4 terms, right? So I'm going to take one of them, and you're going to do the rest of them. Okay? So let's see. If you were to open this up, and I'm just going to sort of do this hand waving down. So there's going to be an alpha square, then there's going to be a -1, right? And then there's this k dot epsilon r, k cross dot k prime cross epsilon s, this term, and then there are 4 terms in it, right? And so it goes like this. So you have a with a, right? So let me write this down. And then, so you have an AR of k and a s of k prime, and then you're going to have e to the I k dot x, e to the I k prime dot x, e to the I omega t, and there is an e to the, by the way, there's another mistake here. This is also prime, right? You guys have to remember that omega k is k, right? And so this is, please let me know if there's a mistake. So this is minus, and this is going to be minus 1. Okay. So, and then there is going to be, this is going to be with a plus sign, then there is an A with a star, RS, then minus a star with AS, and then plus an A star with an A star, right? And so there are going to be these, all these terms. Okay? So let's look at the first one. AR, K, AS, K prime, e to the I omega prime t, and e to the I omega t, and then, okay, so we're going to take this b squared and put it back in here, right? So there is this d3x, there's an integral over d3x as well there. And so, so this becomes e to the I k plus k prime dot x d3x. And what is this thing? Which one? K minus k prime, right?
No, k plus k minus k plus k.
It's chronic redundant. It's not derived into y.
So because
these are
discrete.
Yes. These are discrete. And so this is delta k minus k prime, and there will be a v here. Right? And now you can see why we have a v in alphas. Right? So you'll see that in the end, we have kept the factors in the preamble so that in the end it just works out. All of the things will work out. And that will tell you that the dimensions of everything that is written up there in the first line are correct. Yeah. Sure. So this is going to give you a 0 if this thing is not 1. This thing is 1 only when these two are the same. So this gives you a delta function. And then if this gives you a 1, there is a v for it.
right? Yeah, so, and so, you can basically erase that and make these two the same. Right? Or no, not the same, really minus, right? Okay. So, here is the other factor. So, K cross epsilon R dot minus K cross epsilon S. Okay. Now, epsilon R and epsilon S, epsilon 1 and 2, so R can take values 1 and 2, right? So this is the direction of K, and epsilon gives you the parameterization or the basis in the plane perpendicular to this, right? So it gives you, so this is epsilon 1 and this is epsilon 2. Right? That's what these things are. So if you were to look at this, this is either 0 when these two are different, or this is minus k squared. Right? Smart? You can do it the hard way, or just open this up in terms of epsilons, and then just contract and then see that you will get a delta R or something. Or you could just look at this. I mean, if these two are different, K cross E is going to be parallel to this, and K cross this is going to be parallel to that, and the dot product is going to be 0. Unless both R and S are the same, one of these, in which case it's going to be minus K squared. So it's going to be minus K squared delta RS. Okay? Okay. So now, so you can do all of these terms just like that. I'll give you the final result in the end. And but on the other hand, you still have this to contend with, which is minus partial A over partial B. And let me just write it down quickly. So K R alpha I omega A with the whole thing minus A star, no, sorry, plus minus. Right? It's going to have this structure. And again, when you square this, there's an epsilon. So when you square this, you get sum, all of the sums, okay, and minus 1, and then alpha squared, and then omega squared, and then epsilon R dot epsilon S, there is a sum over K R K prime S, and then 4 terms. And all of the terms inside will be dealt with in exactly the fashion that I've described over there. Okay. The only thing here is that this thing is again either 1, I mean this is delta RS, right? This is delta RS, and so you get an omega squared delta RS, right? Guys, you with me? Everybody? Okay. Okay, so when you do E squared plus B squared, right, you're going to get, I'm not, D3x, blah, 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 whatever. There's a 1 by 2 as well there. Then you will see that in the first term, so you will have these like terms, AA, and then minus A star A, and then minus A star, and then plus A star, right? In these terms, you will get 2 different kind of terms. One whose coefficient is this, and you can see that the coefficient is this. So there is an omega square. So there's a minus k squared, and then there's an omega squared. Right? On the other hand, when you have this term, this has another extra negative sign there. So it's going to give you delta, right? So instead of this delta, when you treat the second term, we're going to get e to the I k minus k prime dot x. And this is going to give you delta k k prime. Right? And so there's going to be a negative sign. This negative sign is there in front, and this will get cancelled elsewhere. We'll see that later. If I can remember. Anyhow, so there's going to be a relative sign here, and then there are going to be terms where there's not going to be any relative sign. And since this cancels out, right? So this goes to 0, and this goes to 2 omega squared. Right? Okay? And there is a sum over k r, and then you have an a with a star plus, oh yes, there's a negative sign here. So this is, this is a and a star, and this is a star plus a star a, and these have extra negative signs here. These negative signs will go over with this negative sign. Right? Okay. So in the end, and you will do this sort of in all glory, like on 5 pages, right? And so, in the end, when you will calculate h, which is a half b3x e squared plus b squared, right? The result that you will get is this. So this is going to be 1/2 sum over kr h dot over 2v omega k. This is alpha squared. Right? This is alpha squared. So here, is this alpha squared?
Yes.
This is not exactly what I wrote yesterday, by the way. But this is c is equal to 1, and there was a square root, and that square root goes away with the square, right? And so anyhow, and then you get 2 omega squared, right? That 2 omega squared coming from here, this 2 omega squared, and you get an ARK star plus A star K. Of course, at this level, you can just simply sort of add them up. This will cancel this 2, right? And so you'll get KR. And so this, and then there's a V, right? This V, K. And so you'll get H dot omega and A R K A star R K plus a half. Right? Or where did the half come from? Wait. So this, no. This is the answer. 2 gets cancelled with that 2. This 2 gets cancelled with this 2. And this omega 4k goes away. Yeah, so fine. Right? Okay. Let's do one more thing. Let's write it first like this. and then like this. Okay. Why do you want to do that?
Because you want to convert in the form that.
So what does this remind you of? He's just going to partner. What does this remind you of? Harmonic oscillator, right? That's why we did harmonic oscillator to begin with, right? This is the, if I just draw it like this, so a dagger or whatever. So basically I should write it like this. That's why I don't want to add them up right now, right? But this reminds you of the simple harmonic oscillator, right? Of course, in the simple harmonic oscillator we have operators. Here these are just coefficients, right? You can just okay. So now comes the punchline. You say that you want to quantize the electromagnetic field. Well, so what does quantization actually mean? So when you guys look at your quantum mechanics the first time around, so how did you sort of reconcile yourself with that? Oh, okay, so this is quantization, right? So what was it that was told to you and you said, okay, this is it. Do you have the homework on you?
Yeah.
Can I see that? Or at the end of the class, show me. Yes. No, I'm asking about the procedure. I mean, what was quantization? What is? Did you ask what is quantization, and you were told that this is just a procedure? I mean, you instead of you take the Poisson brackets, and I don't know how you were told about quantization. There was the H bar just magically appears from somewhere, and you say, okay, this is quantization. So, so what is quantization? What do you do when you quantize stuff? No, that's not what you do. Say again? Yeah.
Place the quantities that are observed in classical mechanics
With operators. Right. So you have operators, and then there are these two canonical operators, x and p, and you just write this commutative relation between them, right? So we're going to do exactly the same. We're just going to, in this case, the operators, the only operators that you can see are A and A dagger, right? And you know how to deal with that because you've already learned it in your quantum mechanics. And you say, okay, if I want to quantize this field, all I have to do is define a vacuum. So first we have these two operators, A and A dagger, right? So you convert this A of K, R, to an operator, AR of K, right? And you have A star, RK, and you convert that to A dagger, K, right? I'm not going to be putting hats anymore. And then you say, okay, AR, K, and AS, A dagger, SK. This is just delta KK prime, delta RS. You see, since we're working with these boundary conditions in a finite volume, it's very easy to work with these things. Otherwise, they'll become Dirac delta functions. They're just harder to sort of think about them. Okay, so this is just easy. Yeah. What else do you want to use? Basically, you could say, yeah.
The electric field has to go zero at the magnetic poles. And the periodic condition imply that it could be non-zero A and have the same non-zero magnitude.
Second? yeah. So you want to say that you want to have the field going to 0 at the boundary. I don't know. Then you would say I could have charge on the surface, and then there would be a jump in the field and all of that stuff. All that you're saying, and this would apply to any field, not just the electromagnetic field that we're talking about. And by the way, we're talking about this boundary in the presence of no sources. So no dielectrics, no metals, no electrons. It's just the field itself. And so these are sort of, so you can think of it as a torus. All that you have done is, instead of talking about the infinite universe, so if I were to draw this, your universe is a torus. So you identify this with this, and this with this. And so that gives you periodic boundary conditions without having to add that the field has to go to 0. This is the same, I mean, there are other modes present, but they will destructively interfere, blah, 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 and the same argument that De Broglie gave for stable orbits of the electron. In, that was De Broglie. Yeah. So you just have to think this in 4 dimensions.
Bohr's model.
Bohr's model, yeah, Bohr. No, I think it was De Broglie who, Bohr first said that it has to, there are certain orbits that just stable. And then De Broglie came up with this idea of why are they stable? Because the wave, the wave won't close on itself and it will destructively interfere and just wither away. And on the only stable orbits will be the ones where you have an integral number of half wavelengths in that orbit. I think it was different. Same one. Okay, anyhow, so you apply these boundary conditions. So you say that you sort of upgrade the status of these two operators with these commutation relations. Where do they come from? Well, this is quantization. This is called canonical quantization. And so just give it to you. So you define a state, which is the vacuum, which is defined by the fact that for any value of R and any value of K, this is 0. Right? And so if you have R and K on this creates a quanta of the field of this momentum, right? So write it like this, and this polarization. Right? And by the way, it goes without saying that if you, well, it is over here, well, that if you have A with A or A dagger with A dagger, all of these are 0. Right? Anything else? Doesn't matter what value of K and R there is. And then, of course, you have the number operator. So the number operator, and this is all that we have done already. And so this is A dagger, K, A, K, right? And the eigenstates of this operator, how should I write this? N, R, K. These are written as A, R, dagger, K, over, and whatever this n is, and R. Right?
So all of this works on the same polarization, the same mode. we have like different nodes, then these operators would not behave this way.
Very good question. Excellent question. What did he ask? What did he say? Repeat the question.
Would these operators behave differently if we did not have the same polarization as the same node for subsequent operators?
Well, okay. First time you asked slightly different question. Oh, yeah. Yes. Or I understood it slightly differently. What he's saying is that what you have created here are just sort of, if you want to call them particles, these are photons now, right? Because they're quantized. By the way, that's all there is to photon. But anyhow, so what he's saying is that what you have created out of this vacuum by the application of this are just a certain photons of certain energy and certain polarization. Right? Where are the other photons?
And just change the values of R.
So then what? What? I think what he's asking again. What should he be asking? Well, you want to rephrase the question?
No, like to create photons.
Now, how would you change R and K? This is the state that is given to you. This is a state. That's it. That's the state. What do you mean you keep changing R? What happens if you have 10 photons, all of different mixed polarizations, different polarizations, and different Ks? What happens then?
The state would be different. I mean,
Yeah, what would it be?
get the product of
So then the state, what I'm trying to say is that the state is going to be a linear combination of things like these. So for example, you could sort of NSK1, NRK2, and blah blah blah, however many you want. And they will just be tensor product of Ri. So yeah, N R I K I. That's what you asked me, right?
Kind of.
Yeah.
So, and by the expression A diagonal N.
Yes. Absolutely. Okay. So these are eigenfunctions of this and consequently of, oh, I didn't even write that? Okay, so then Hamiltonian is just, K, let me write it like this, KR and H dot omega K N N of K plus a half, N of KR. How do you write this? Like that. I wrote N sub R of K plus a half. Right? Okay, so these are eigenstates of this operator and consequently of this operator. In fact, these are eigenstates of H. What are the eigenvalues here? What are the eigenvalues? H cut omega k n sub r k plus a half and then sum over k r. These are the eigenvalues. Okay. So basically what you have here is a superposition of independent oscillators.
सर आपने जो यहाँ हैमिल्टोनियन लिखा है इसमें आपने हाफ क्यों लिखा है क्योंकि ऊपर से जब हमने हैमिल्टोनियन आया तो वैक्यूम टू जीरो एनर्जी
नहीं, इसीलिए तो मैं बार बार इसको नहीं लिखा था। ये यहाँ से आया। How would you know if to write A star or A star A? The only thing that you can do is treat them on equal footing.
सर प्लस हाफ लिखा है
प्लस हाफ नहीं आया ना?
सर नीचे नीचे जो आपने हैमिल्टोनियन लिखा है अभी उसमें आपने प्लस हाफ
ये वाला हाफ, ये वाला हाफ यहाँ से आया।
ये यहाँ से
ये वाला कहाँ से आया? ये भी कॉम्बिनेशन रिलेशन से आया।
सर इसका मतलब वैक्यूम स्टेट एनर्जी है लाइक जीरो
वो
स्टेट
तो बाद में देखते हैं क्या है। वही है, जाएगा वही। क्वेश्चन है कि आया ही क्यों? क्वेश्चन तो ये है कि आया ही क्यों? कंपेयर तो हमने किया, लेकिन अगर आप उसको भी ऐसे ही लिखते थे, if you were to write that, for example, if you were to write the harmonic oscillator,
सर ये इसमें तब भी हाफ नहीं आएगा क्योंकि
सो उसमें एक एक्स्ट्रा हाफ का फैक्टर
एक एक्स्ट्रा हाफ का फैक्टर होना चाहिए क्योंकि n हर्मिटियन ऑपरेटर है तो ये दोनों ऐड हो जाएंगे बस हाफ अलग से होना चाहिए
इसको जब करेंगे तो ये ऐसे नहीं हो जाएगा, a dagger a plus a half,
सर ये कैसे होगा
नहीं यहाँ पर एक हाफ ऐसे रहेगा।
कौन सी
ये ऐसे है ना,
हाँ
ये ऐसे है।
अच्छा
इस तरह की बहुत सी चीजें हैं, just go home and just work them out, right? Otherwise, we haven't shown, but you can later on will show that this is the momentum operator. This is the momentum operator, H cut K and N R K plus R. And the eigenvalues here are going to be again H cut K, N R K plus R. Just writing this to, so that you know, and you already know, but so that you know formally that the field carries momentum as well, right? And so, questions here? Okay, so this is a general state, right? A sub R sub K. This is a general state, right? And what if I were to take one of these A's and apply it here? What is the answer? Second? Oh, yes. Yeah.
Square root of NR K times water.
Yeah.
We have to specify the R and K of the operator.
Yes, then what?
Then
X,
the
yes,
X of the
then what?
so the X of the corresponding K.
Yes. And if that particular photon is not present in your superposition, what happens then it goes to zero, right? Otherwise, if you have NR sub K, then it's pick out, and you know how the tensor product works. The corresponding operators just find their own state and add there. And so this is going to be NR of K square root, and then this is going to become NR of K minus 1, right? And then so, one quanta of sort of energy will vanish from here, one quantum momentum will vanish from here, the corresponding momentum energy. And hence, the annihilation operator, or annihilation operator, whatever. Right?
So in the case where that particular position and mode wasn't present in the state,
Right.
and if I apply an addition operator on that whole state, and the whole state just collapses, and then this goes away, it goes to zero. So that's really weird. Like I'm not even working with any of the other polarizations. It just exists in
Isn't
the
that
field.
weird? Yes, without one. They were smiling. What are you asking, guys? Yeah, why are you smiling? That's not the right question, right? Yes. What did he ask? What did he say? What is the application of A mean actually?
Okay, sorry.
Of A. These are not eigenstates of A, right?
So no.
It's not like you're calculating the momentum or the energy. It's just an annihilation operator. If it doesn't find what it's looking for, it just gives you zero. It's not that I'm saying that once you apply this, you take the same thing and apply some other A, it'll always give you zero now. That's not what it means, right? It's a state. On that state, A has an action. The action of A on this state, if it doesn't find a corresponding photon in there, is to annihilate it. That's it.
So you just lose the whole state.
What does it mean that you lose? You still have the state. You can write that state again on the piece of paper
But
and apply another A or A dagger on it. What do you mean you lose it?
no, but if this operator just
Yeah.
like if I have a physical state, which
Okay,
operation not
Just a second. This is a state. This is a state.
Yes.
You apply A on it, you lose it. What does it mean?
I mean, that state doesn't exist anymore.
No, it does. It's still there. The action of this operator on that state is just zero.
What does it
It
mean?
doesn't mean that there is poof, no more universe, there's no more vacuum. You shouldn't have applied that operator, dude. Now you can't create any more fields. The state is there, the Hilbert state is there. In that state, this would still continue to exist. The action of this on this state is zero.
What does it mean for some operator to have an action on a state when it fits?
Whatever it means. I mean, if you have an operator and a state, it will give you some other state. That's what it means.
That's the new state, right?
Right? So this gives you zero. Zero is possible.
Zero is my
So
state.
you could say that zero
Yes.
on this.
But this state has no amplitude now. It has like it doesn't
no-
exist
it's
anymore.
just
ये वैक्यूम में मतलब कोई फोटोन है ही नहीं, तुम उसे एनालाइज कैसे करोगे? फिजिकली इसका कोई मतलब नहीं है, मैथमेटिकली इसका डिफाइन नहीं। There is no photons, you cannot annihilate.
It's not an observable, that's the right thing that you're saying. It's not an observable. It's not like you're saying that it's a process that is given by the observation of this operator. So for example, you could say, oh, I apply H, and it just gives me not back this state, but it just gives me zero. Everything's gone. By the way, when I used to teach, I think I taught quantum mechanics to a couple of times, or maybe 3 times. There is this notion in everybody's head that the application of an operator on a state is equivalent to measuring that operator in that state. That's not true. That's not true. Right? It's only in the eigenstate that the application of the operator results in an eigenvalue.
Even that is not a measurement.
Even that is not a measurement. Right? Measurement is a violent, completely different process, and it doesn't have to do with the operator except for the eigenvalues. Right? Because measurement is always going to return one of the eigenvalues. That's it. The rest depends on the state. Okay, so here's a problem that Usman already alluded to, and or maybe somebody else I don't recall now. This thing has no particles, right? But it still has energy. Right? As somebody just pointed out, that if I were to take h on this, it will return me this value. So if I were to measure the value of h in this state, it will return me this value. Right? Maybe that's where you can get this idea. Application of the operator gives you. Right? So, but you just take this state and you, the only eigenvalue possible here is E0. And so, and that thing, E0 is 1/2 sum over k, sum over r, h dot omega k. And what is this equal to? Yeah, this is an infinity, right? Because there are as many modes as you want. Okay? This keeps on going, never stops. And as actually k increases, this increases in magnitude. By the way, in quantum field theory, you will get infinities not just because of the large k, but also because of the small k. One of the other things that happens when you put the field in a box is that you get rid of these infinities at the lower end, which are called infrared infinities. These are ultraviolet infinities, okay, because of the high k. And so there are many advantages of using these boundary conditions. Anyhow, so the usual way that you deal with this, if you're not thinking of gravity, then the usual way you deal with these is, yeah.
So were we not using finite case? Like initially we defined a box.
Yeah, that's a very good question. Why aren't we using that?
Because we are in a box and we have a finite number of modes of the field in the box.
So then it shouldn't be infinite,
Yes.
right? Sharpen. So, anybody apart from you, three, or whatever? Smart.
Sir, I don't think they're not infinite in a box. I mean, you have countably infinite modes in a cavity or in periodic boundary conditions.
Okay.
Basis.
Basically gave the right answer. Did you understand what I said? So जब आप box में उसको डालते हैं, it doesn't mean that you have finite number of modes. You have a countable number of modes, but that's still a countable infinity. There is no largest value of k. There's the smallest value of k, but there is no largest value of k. Okay? And so as you get infinity, yeah.
सर स्मॉलर के होने से इंफिनिटी कैसे होगा, मतलब आप जैसा बोल रहे हैं
वो बाद में देखेंगे। अगर आपके पास log आ जाता है तो log of 0 क्या होता है? Right? If you're solving an integral, you get a log 1 over k या 1 over k स्क्वायर का इंटीग्रल लेंगे आप और आपके पास 0 हो एक तरफ, what will happen? Anyhow, so what is the usual way of dealing with this? If you're not talking about gravity,
Ignoring it, redefining it as a
ignoring what? Well, you can't just ignore it.
redefining the vacuum state to have zero energy.
Zero energy. What does it mean? Why don't you define any state to have any energy that you want?
We have ladder of states. So we can just redefine the lowest step on the ladder.
Yeah, that's zero. Right. Yeah. So you're just saying that we're going to measure energies starting from wherever this infinity ends. So we're just going to measure the differences in energy. Okay, so for example, you can, I mean, it's the same thing as saying that only the differences in potential are measurable. So you can assign basically infinity of voltage to any point. If the other point is infinity plus 10, then the voltage difference is just 10. Right? So, but this is really, what's the problem with this? Of course, in field theory and in in the usual settings, it will not have any problems, but this will contribute to the cosmological constant. Right? So basically what you're saying is that if everything, I mean, if there's an infinity of energy everywhere, gravity doesn't care which kind of energy you're talking about. It is going to respond to it. And so there basically should be, I mean, the curvature should be of the order of, let's say if you even have a, as he was saying that if you could just, well, maybe he was saying or not, I don't know. But you could put an upper limit on K. Let's say that we don't trust this expansion and all that stuff to, let's say, after the Planck state, right? Shorter than the Planck length. So let's just put a cutoff, just like you have, because of the size of the box, you have a smallest K. You can have a largest K because of this smallest length that you don't trust your theory after. And so, still, this would not give you an infinity, but a very large number, right? And the curvature of the space-time will, of course, respond to that. And so, you, for example, if you were to put a cutoff at the Planck length, you would get a curvature of the on the scale of Planck length, right? So there would be appreciable curvature on that size. And so the universe would be very curvy instead of this being very flat. And so you can, and this is sort of, by the way, this is coming from a relativist, so if you talk to a particle physicist, they wouldn't care about it. And so, but for me, for example, it tells you that the formalism, and basically this is the formalism. This is how we're going to quantize all of the fields. And this is the formalism, and this is going to be present always. And so that tells you that these kind of infinities, and there are other kinds of infinities that will appear later. We'll talk about renormalization and stuff on that. These infinities tell you that this is a very sort of effective sort of treatment of the quantization of fields that you're doing. You need something much better. And basically, all of these problems, when we say that, oh, can we put a cutoff at the upper end, blah, blah, all of these are problems of quantum gravity. And so, but unless you understand all of this, and the problems, and GR and this problem, because GR you have singularities as well, right? Black holes. And black hole is a place where the space-time ceases to exist. And so you have these things appearing because of these, mostly because, you would say because of continuum. Okay? And so, but anyhow, maybe I shouldn't say too much on that. Second, it's not part of the space-time thing. No physical laws apply there at that point. The curvature, I mean, there are event horizons around a black hole, and so nothing comes out of that except maybe Hawking radiation. But if there were not, then an elephant could come out of that, and you would just have to live with that. There is no way, there is no physical law that prevents the emergence of an elephant out of a black hole, because no physical law apply there. A whole universe would come up. Right? So, or they could just be conduits in other universes.
Even when a black hole sucks in matter, it glows now. Conservation of its matter property.
हाँ, उससे तो कोई मसला नहीं, लेकिन उस पॉइंट पे क्या हुआ? उस पॉइंट पे क्या हुआ? वो पॉइंट जो है, वो आपके स्पेस टाइम का हिस्सा नहीं. So these are all problems that are appearing in that people are very aware of for the last 70 years or maybe 80 years or whatever. But and that's why there was this big push on quantizing gravity, which means quantizing all of this stuff with gravity, and no one has been able to give any framework which has been remotely successful. I don't see it. There have been many frameworks to talk about quantum gravity in, but they don't sort of, they're just frameworks and don't sort of give you any. Yeah, because that would be a harsher statement, but yeah, I would say that it don't work. Okay, so one last thing. What is this? Is this still infinite? Momentum.
Find the operator, it has some momentum.
Yeah.
It will have some momentum.
Yeah.
H bar k.
It will have some momentum or infinite momentum or one momentum?
Infinite momentum.
Infinite momentum, right? Turns out that this thing does not have a problem. It is still zero. Why? Because for every k, there is a minus k. And when you sum those all of those modes up, you still get a zero. Right? But also, I forgot. So what will happen from now on is that we'll call something that is called normal ordering or whatever. I'll talk more about it. But what happens is that you just forget about this half. Right? The first time Parvez did that in class, he didn't like it. He was teaching us quantum field theory. I think it was maybe master. He came on the board and said, "Why it doesn't exist?" I said, "What? You just wrote it down." By the way, there are observable effects that we attribute to these so-called zero-point energies. I don't think that I have time to go further ahead. Can you give me the homework? So, for example, by the way, the reason I crossed that off is by claiming that it's not observable. Okay? So you just observe things on top of that. So, for example, Dirac would say that you have an infinity of particles, and then all that you do is that you take one of them and bring it up, and then whatever the energy difference is, that's what you measure, right? That's what you measure. But for example, so if you take, you know what a cling wrap is, right? You take two sheets, and you put them together. They cling. Why do they cling? That's the Casimir effect. Everybody knows about that, right?
I heard it first, but I know there's like.
So even if you say, "Oh, maybe cling wrap is not so good," you guys know about the transparency that people used to use before the multimedia, right? They would, and if you see somebody, some old guy who still uses them, if they have to bring them out, they first have to tear them apart before they can put them on the projector, right? They just cling, or they put pieces of paper in between, some rough, slightly rougher piece of paper, so that they come out easy. So most of the time when you ask people why that happens is that there is pressure, air pressure, right? You do that in vacuum, still same thing happens. And so sort of the explanation that people have come up with is that the number of modes inside and outside, there's a difference, and there's a pressure, and that is attributable to this zero-point energy. Yeah, please. Homework. You sent that, right? Yeah. Okay, so let me tell you the problems that you should attempt. So number one, write it down. 1, 2, and don't be put off by this SO2 transformation. There's just a transformation given, right? You know the rotations in a plate, right? That's SO2. And so all that you have to do is that write down 5 primes in terms of phi, put them back into L, and show that you get the same expression for 5 primes as well. So it's invariant, that Lagrangian. Then most probably in the next class, next week, I will sort of review a little bit, maybe for half an hour, the classical field theory. And Junaid is also going to have a class on Monday, right?
Yeah.
On
Around 5 p.m.
around 5 p.m. Classical field theory, right? Review. And so, if you want, you can do question 3 after that, or you can try it even before that. I mean, all of these RED guys should be able to do it. Okay. So, then 4, you can do it next week. Question 4. Yes. 5, you can do next week. 6, you should be able to do. Okay. Should do 6 this week. 7, you should do it now, this week, and 8 as well. Forget about, 9 after the second week. And then, yeah, and then there are a couple of problems from Mandel and Shaw. So you can do both of the problems, problem 1 and maybe problem 1. This is chapter 1, problem 1. Problems from chapter 2 and problem 2 you can do later. Okay. You don't have to turn these homeworks in. They will just be checked in your quizzes, whether you have done the homework or not. And there could be a quiz at any time. And any questions?